welcome.
Thank you. Right, I'll try here. Yeah, it's really a talk about tools and tool use. I'll wait, just take this off here. Yeah, is that on? Is that on? Hello? That's good? Yeah. Okay. So, I am a research fellow at Falmouth University at a research group called Autonomatic. We've been going for some years now, and we are all craft practitioners as a background, although we are in academia now. So we make stuff with new technology. We got new technology tools. We got a range of machines there, all computer driven, which we've been experimenting with over the last. Well, we established in 2004, so 9 years. But my background is in craft. I'll put this slide to show my pedigree. It's not me, none of those guys, but it's my background. The guy on the left is Leif Wange, who was my pottery tutor in Denmark. I trained as a craft potter, a traditional apprenticeship in Denmark, and that's just to show where I come from in terms of, but to kind of highlight the connection with craft and technology. There's a film called The Mark of the Maker. I'm not sure whether you've seen it before or you're familiar with it. It's a great film. It's available on Vimeo, so you can look it up straight away. It's about a couple that set up a handmade paper, little handmade paper company or little handmade paper workshop in the 80s, and then there was a film made in 1991 about them, and it really sort of encapsulates some of the core qualities of craft practice. And there's a couple of quotes I'd just like to show, a couple of clips of this film that I like to show.
The thing about industry and mass production is that it's set up with tools and jigs and things so that if the operator gets the piece anywhere near the machine takes over and finishes it. Whereas when you make it by hand, if you lose concentration, you'll destroy the piece of paper or mess up the suit, a pair of shoes or whatever. So, you know, it's all relative. And I think when something is made by hand, it's somehow or other, it has the mark of the maker in it.
So it's all about the hand and the risk and the skill of the maker. That really, for me, just kind of that's the key issue in craft practice. But I think he's being a little bit disingenuous there. It's Howard Clark and his wife's called Katrin. And actually, early in the film, he talks also about tools, because one thing is the hand, but nearly all craft practitioners use tools of some sort, and he has some reflections on them creating tools, specific tools for their practice, which doesn't exist. I'll show that film now here.
People who visit Twin Rock are often surprised at all the machinery. You know, we're supposed to be making this by hand, which is an interesting thing. What's the difference between handmade and machine-made? Here in this shop, I made about 40 beaters and 60 presses for other paper makers. And somewhere along the line on each one, I bled on them because if at one point or other I'd get cut and bleed on the machine. And yet, you know, the reception of it was that it was just a machine, but it was a handmade machine.
Okay, so here we go. It's about hands and it's about machine. It's about customizing machine for that particular practice. And this is really what I'm going to talk about now, the use of the hand and making tools and machines in a context of a craft practice with digital tools. One of the very so the first kind of topic is using the hand with digital fabrication tools. And I trained as a potter, and the use of the hand in pottery is obviously ubiquitous, and the kind of throwing is fantastic. That direct interaction with the hand and use the hand is a fantastic way of making. And very early on, when I started exploring digital tools, I wanted to try and see whether that kind of use of the hand could be replicated or used in the context of digital tools. So we quite early bought one of these things here, which is it's a motion capture glove, and it works on these the base of these blue tapes. They're fiber optic tapes, and when they bend and twist, then the data is sent to a computer. I'll show you a little film about that. So there you go. When I'm bending and moving my hand, that whole movement and motion is captured and into in a computer program. It's used mainly for animation and special effect, where actors would wear this kind of kit and then they record the movements and then put on a character, like for example the Gollum in the Lord of the Rings. That was done like that, where an actor would wear a suit like this. But I wanted to make with it. I wanted to use that as a recording device. And what this is what happens in the computer. The green thing is me, and with the hand, then you can select points on the recording where you want to track. And in this case, it's the fingertips. And then they create trajectories. These black lines, which are the movement of the hand. And then when you got those lines, then you can use those lines to create a form in the computer. You can use them as kind of just like the Tipi here, like the frame here, and then you can kind of stretch a virtual material between the lines. So the yellow stuff you see here, in this case, it's the blue stuff. Once you got that, you then got a form, and then you can process, or you can make. In this case, we didn't use a rapid prototyping machine. We used a CNC mill. CNC stands for computer numerically controlled, but really just computer controlled machine. It just grinds out from material. So there you go. You put a block of foam in, and it grinds out the shape that I've described with my hand and my fingers there on the right. So as a potter, I thought this is great. I can describe form with this new way of recording, and I can make some really expressive pots without the kind of need to consider the material and kind of really be expressive with my hands. But it really didn't work very well at all, because there was once you record the form, you milled out the shape, all fine, and it was quite straightforward. But then you had to mold make. You had to kind of create a plaster mold of that form, and that was cumbersome, and it was lengthy, and the piece would never stand up because you're working in mid-gravity and there hasn't got any reference, and it cracked in firing. So it really didn't work very well at all with ceramics. Instead, I created some seats, and the surfaces of the seats are milled directly in a sort of artificial wood material. It's called milling board. It's actually quite beautiful. So you mill the form directly in there, and you don't have to deal with all the kind of drying and shrinking and not standing up. So it worked much better with the furniture seats here. You can see 5 lines. So the 5 lines are tracked from each of the fingertips, and it's obviously quite bumpy, and that's intentional. The idea is, the rippling you can see is the trembling of the fingertips. So the intention with this piece and this whole exploration was to try and see whether you can get the same kind of concept from hand-thrown pots on the wheel, where you leave the evidence of the fingers in the piece. You know, that's a part of the aesthetics. That's a real part of the connection with the user or the buyer. And the same thing with the seats. In this case, you just experience it with your backside rather than your fingers. But that was the kind of the idea with this particular exploration. The shape hand, that motion capture glove which you saw earlier, after lots and lots of try, I really struggled with it, and I found out that it really wasn't very accurate at all. And I emailed the manufacturer, and then after all this, after a lot of kind of conversations, what are we doing wrong? There's settings or whatever. And they said, well, no, actually, you're right. It really isn't very accurate at all. It's mainly used for film and animation. And so it became a really bad way of, because you as a craft practitioner, you really know where your hands are. You really know where you're very good with your hands. And to have a recording device like the glove that didn't record accurately your movement of your hands, it really wasn't very good. So I moved on to a different device to try and explore this territory, and this is called a microscribe, and it's like an arm, and it's very accurate, and it's very easy to use. It just plugs into the USB into the computer, and it records in 3D. Its intention, the intended use for it is to record shape and for industry or check the tolerances of things manufactured in industry. But so it's not really used as a kind of input device. But that's what I started using it for. So I could describe rims of bowls, coming back to ceramics or pots again. I could describe that kind of line, just the perimeter of the bowl with it, just one point. And then that would be recorded straight into the software program like that, the red line. But what do you do with that then? That's not a bowl. So part of this exploration or investigation was to see how you can create a complete making sequence based on just tracking a line or describing one line with that microscribe arm. So the process I came up with was that when you got that line, you can extrude it. So you got a surface. It's very simple stuff, this. And then you can unroll it. So you just flatten it like a long sheet of paper. And once you've unrolled it and flattened it, it becomes much easier to process, because then it's a two-dimensional shape, and they're much easier to deal with in terms of digital fabrication rather than three-dimensional shapes. So you can get it laser cut by a friendly local laser cutter, and that's there, laser cut in beautiful stainless steel. And you can also laser cut the top protection, where you see it from the top. So that now you've got two representation of that line, and if you put the two together, like that, then you get the three-dimensional representation. Again, that three-dimensional line, that's the edge of that stainless steel color here, that line I've drawn in space. And the reason for battling to get that piece of stainless steel into that color is that stainless steel can stand temperatures needed for forming glass. So all of a sudden, you don't have a stainless steel cutter sitting in a MDF top. You have a refractory mold. If you put plaster around, you put the whole thing in the kiln, you cut a round disc of glass, you put it in the kiln, and you heat it up, and the gravity and the heat just makes the glass dome and sit down on that edge. So all of a sudden, you got a piece created from that line drawn in space. So this piece here, you can see the overhanging glass here, that's just surplus. But the line, the input from the hand, is that red one there. So the piece is created purely by the input of the hand, and then the process of the glass and the heat in the kiln. There's a Crafts Council made a film about that, so you can go online. There's a film about that, so you can see that. There's more information there without me banging on about that. But to come to the next section of the talk, what I was making was actually pieces. The glass pieces were made very much by normal kind of analog craft processes. What I used the digital tools for were not to make the pieces. I used the digital process to make the tools for the pieces. These are the tools, the molds. They're not the actual pieces. So, next section, making new tools. A lot of the tools we use or have used at our research cluster, we were very spoiled initially. We had EU money, so we bought lots of expensive, really lovely kit. And for a long, long time in digital fabrication, it was impossible to get anything apart from really expensive industry-made kit. So that's what and it's only by being in a university environment that we could use it, we could afford to use it as a crafts practitioner. But things are changing now. mainly due to this project. This probably already has been described. Has it been demonstrated? It's been demonstrated, yeah. The RipRap project from University of Bath. We created an open source rapid prototyping machine. That blew open the whole kind of digital fabrication to a much, much wider audience and completely changed the price structure of the kit available. So that's been fantastic and inspired lots of people to use digital fabrication, and it's now much more widely available for anyone really. There's other projects might also been described. That's the laser sour, which open source DIY laser cutting machine. There's the SAN, which has been mentioned earlier, Kaiser. So there's people that are making their own digital fabrication tool now. And also Enrico Dini from Italy has made this really large-scale machine for making stone pieces. But again, an individual making his own tool for digital fabrication. So it's a really, it's just a booming thing that the information and the access to knowledge to make these this machinery, which previously were really expensive and hard to get at, is just out there. So, in 2011, we thought we'd fallen a little bit behind the curve in this, because we had all the kit, and so we can't, you know, it's great, we can use it. But actually, what was happening out there was a lot of people were creating their own kit. So in 2011, we thought, right, we're going to try and see whether we can also start making our own equipment. So we organized a CNC machine building workshop, 3 days, just 3 days. And again, CNC, computer numerically controlled. So we had 3 days to build a couple of CNC machines. And we started pretty much from scratch. What I should say, there's so much online in terms of how to do these things, but actually to do it and to get to learn from somebody is incredibly valuable. Just to wade through all the information that's out there. What's good and what's not so good, and what's the thing to do. So we did. The guy here with back to us, or he's also here on the right. He's called David Turtle, and he is a technician at the RCA. In the metalwork and jewelry department, and he has built a few machines. So what we did was to get him down to actually to create these sort of things. You can do it from online, but actually I would recommend to get somebody down that you can learn from. It's very important, I think, that human kind of, and just to kind of, instead of having to trawl through all the internet stuff. So I think learning from somebody is really very valuable, and that's really valuable to us also. But we started from complete just elements. These elements are available from the shelf. They're sort of standard machine building element. They're very cheap now. A lot of stuff's coming from China. So you can buy these aluminium extrusions, cut very accurate to size and square, and they'll be delivered to your door, and they're very affordable, very accessible. So we're building the machines. So it's pretty much just like large scale Meccano. And there we are. That's a sort of standard 3-axis CNC machine, and that's a rotary machine that is a digitizer. So it kind of has a probe. I'll show it in a moment. That records the shape. So we tried to build 2 machines, and it worked very well. This machine here on the left, we explored the use of slip to pump slip through this channel here, and actually draw with slip. While we were doing it 3 days, that worked okay. But really, the first thing was to explore it with drawing. We made we put a little pen on it. This is the first run, or a little brush actually, so we and that little action is just up and down. So it's drawing things. The first thing, it's a great way to test CNC machine, just to draw, because it's quite a forgiving thing. So the first kind of target was to get them to draw things. So this is a drawing by Katie Bonnell, who was part of the team here, and you can see see, this is the drawing that she's drawn by hand, then scanned in the line drawing, and it creates a certain character through the through the CNC machine, that kind of action of the brush going up and down. It's a rider going over a fence. This was the other machine we made, a rotary thing, a rotary digitizer. So it's got a turntable there, and it's got a little probe there. I'm very proud of that probe. I made that probe there. But the methodology, to use a very academic term that we use for this workshop, is that we didn't have any drawings. No drawings. We make things. Less theory and making. So we just get on with it and we make things. So we needed a probe. I'm just we just initially tried that thing. We didn't kind of sit down and draw things and then engineer things. We just made them. So they're made from the red bit of the probe is a drawing pin, and the other bits are just I think it's and lots and lots of hot glue everywhere. So that's really the approach that you create through making, rather than you kind of have a drawing or an engineering kind of and that's I think that's a very craft approach too. So there's lots of parallels there too. Oh yeah, this is the digitizing machine. So the little point comes in, and the rubber band is also essential, otherwise the pin flies out. And it turns the head around and then it creates the points from the head, and so you could recreate that head in the software, and you could, you can alter it and then do other stuff to it. So that's that's that one. Okay, tool making. Now, coming back to maybe the initial part of the talk, there was this last section was all about making digital tools. But digital tools, as you saw with the glass project, can be used to make analog tools too. So digital tools can be used to make tools that really has no kind of the intention is to use them in an analog way, and they're very good for that. And I think a really overlooked area too. The project that would illustrate this is a project I've been obsessed with for the last couple of years, or more than that maybe. It's a principle called reconfigurable pin tooling, and it's been around for at least 150 years. It's very similar to the one with the toy where you put your hands into it and it comes out the needle thing. But engineers and inventors have been exploring this seriously for at least 150 years as a way of making molds, which can change. You can reset them, so you don't have to have one mold that just make one form, but they can come back. You can change them and reset and make a different form, and it's called reconfigurable pin tooling. That's the kind of engineering term for it. Lots of people have tried, but no one's really kind of found the right application for it yet. They've tried really, heavy engineering ones, steel pins to shape metal. There's an RCA student a couple of years ago tried to do it with slip. So people have explored it, but not really found a good application for it yet. And I've also thought, this is a really good idea, and I want to try it. So I made a tool, a reconfigurable pin tool with pins in stainless steel. So you probably know where that's going. That's going in the kiln. So you can set the form, and then you can slump your glass into the form, and the pins will then form the glass into that form, and it kind of worked. I used digital tools to. That was the kind of maybe the initial point here that. I wanted a way that I can go from a form I can go from a CAD design into another form without using rapid prototyping, but another way, the tooling way. And so you design the form in the software. You then get the CNC machine to push the pins into position, and then you form over that. And what I did, and I think that's also one of the kind of game changers in terms of using digital technology, is that there's tools available now that there wasn't just a few years ago. There's in order to set the pins, you need to know the kind of location of them, and there's a little software extension to a drawing package called Rhino, and the software extension is called Grasshopper, for unknown reasons, but it's a little scripting program. So it enables people to write little programs, not write little programs, but actually put them together. And it's a bit like Lego for coding, programming. You don't have to write reams of code. These are blocks. And I'll show you the next picture here to make more sense. These are blocks that do stuff, you know. So there's a scale, pin, rotate, and you just you kind of drag them in, and then you draw a line. And these lines here is the data flow. So the data flows from left to right. So it's scripting coding for people that doesn't know code over there like me. So it enables me to create the position of the pins and get the CNC machine to do that. So it's just such a learning curve to learn to code. But with these kind of, it's called visual scripting. You can do it, and mere mortals can start creating their own little scripting or little programs. They'll do things, little tools. They'll do things, and I use it a lot now. And they can become really big and cumbersome. You can see one a scripting. It's called a definition over there to the right, and I use it to create my tools, my pin tools. This has not been drawn, but it's been scripted. This means that if I want to change the number of holes or the proximity, I can just do it in the little slider or the other details. It just means that you can always go back, and you can always kind of you can change things very, very quickly. It's a really, really powerful way of working, and it's free. The little extension Grasshopper is free. So I can make these pin tools. This is a round one because I've got a round kiln, so that makes sense. And I can get a laser cut. That's the other thing that I think is a real enabler. There is now bureaus around. This is Loftman Engineering in Tiverton. They're great laser cutters. They also got water jet cutting. But you can just send the files to them, and they'll create my really quite advanced and well, I would say they're very, very accurate, the laser cutters, and you can make tools that are at engineering tolerances as an individual maker, and I think that's a very, very significant that you now get the access to machinery that can make bespoke tooling at a really high tolerances, and it's not expensive. You send your file, and in this case, you know, through to be cut in stainless steel, and they take about a week, and you pick it up. And Holly there, who's my friendly laser cutterist. So that's been a real enabler for me and other craft practitioners that you can get your tools done to a really, really high level of engineering. Coming back to the core project here, when I started. When I started this project, I thought it's gonna work really well, and it kind of did. But one thing that I forgot was the material. The glass didn't like being just forced into shape. The glass liked to do what it liked it to do, and so actually design a shape and then try to replicate it completely through that reconfigurable pin tooling. It really didn't work particularly well. It only started to work well when I started kind of exploring what the glass wanted to do, and this is some of the experiments where I'm trying to force it into the tool. See, it's only reached a couple of pins down here, and up the end it's reached all the pins, but it really didn't like it. It was only when I started using less pins and actually got the glass to do what it wanted to do that it started working. So the fewer pins within reason, and just letting the glass flow, and just looking at what the glass wanted to do, that was really the key to this project. And in the end, now I don't use any digital tools to set the pins. I set the pins by hand. Here's a little film about me. It was made for a exhibition in the States. But I simply just I take photographs of each setting, and then I reset the pins. But it's really all about knowing the material and using the knowledge of the material to use this tool. And digital technology was involved in the tool making, not in the tool use in this case. But without the digital tools, I could never have made these tools to these tolerances that it's needed to be made to get it to work. and I make the pieces upside down because they look better. And I show them and sell them. This is a collect last year. So it's really great to do these projects and actually put the pieces out there and get people to buy them for what they are. That they I'm very happy to explain the processes, but actually that people buy them for their beauty, and the technology behind it is, in that case, less relevant, but they have been facilitated by that. Okay, the last project I want to talk about is using craft knowledge to develop new tool uses. I think we have a lot of knowledge. We have a lot of knowledge about materials and processes, which really have a lot of relevance in developing new tool uses, also for very high-tech applications. And this project, I've been working with Gail Mathias, who is a senior lecturer at University College Falmouth. She is a glass artist, and she has, before this project, she didn't use digital tools at all, but she really knew about glass and casting. And she knew about a particular method called ceramic shell, but yeah, I think Robin, you feature here. Yeah, you're in the red. Okay, so Robin, you're a metal caster. You use ceramic shell all the time for metal, but for glass, it's a new thing. Very, very few people use it, and there's been a PhD exploring it, and Gail worked on that PhD because you have to adapt it for glass. You can't just use the same processes directly for glass as you use for metal, because the glass will contract and all sorts of things. But it's a very good, and Robin will probably concur, it's a very good way and efficient way of casting. So it's very attractive. So we thought we'll get together, Gail with her knowledge of ceramic shell for glass, me with my knowledge about digital technology, and see whether it could work for that. So we have a RP machine at Falmouth. We rapid prototype or 3D print a couple of forms out, and we kind of start exploring that and using the ceramic shell specifically adapted for glass to test it. It didn't work very well. What happened is that the ceramic shell for glass has to be slightly softer in order for the glass to contract and doesn't break. But when you have to heat up, it's the same process as lost wax. You have to heat up and burn out the pattern, the 3D printed pattern. You have to burn that out before it combusts its plastic. It's also very nasty smell. Before it combusts, it expands slightly, and with the ceramic shell that is slightly softer for the glass, it cracks the mold. So we really couldn't get it to work very well. Instead, we started looking at a different 3D printing technology. You might be well aware of it. It's been around for a long time. It's called, it's from a company called C Corporation. It's C Corp. And it builds instead of plastic, it builds the object in powder. It lays down layers and layers of powder, and it spews out a binder. It's the same technology as inkjet printers. It's even the same print head. It's an HP print head. So it lays down a thin layer of powder, and it spews out. In this case, it's a blue binder, but normally it's just colorless. And layer by layer, it obviously builds out the object. That's the object that's just been printed, and the powder that hasn't got the binder on can be removed by blowing, and then you can get the piece out. And again, with 3D printing, or rapid prototyping as it's also called, there's no geometric limitations here, which is fantastic. So this beautiful medallion here, as it is, with the link, the chain link, you can print all these parts in one go. So it's just, I'll just finish that. So there you are. So it's just like any other 3D printing or rapid prototyping, but it builds in powder, and the powder can be changed. The powder that's not used very much in this case. It's a starch-based powder, so it's actually it's an organic powder, and we thought, great, we'll get some of that in. So we have some sample pieces here made in that powder, which is starch, and then you can burn it out just by using torches. You don't have to put it into kiln. It didn't work particularly well. The surface was very rough. It's a really poor quality surface. So quite early on, we thought this is just not very good. It did kind of, you could burn it out. It was fine, but the surface quality was not good enough, and you can use the ceramic shell okay. But I should say these starch samples, were supplied by a company that sells this machine. We didn't have a machine like that at the time, and they wanted to sell us one. So they supplied the samples for free because they wanted to sell a machine, and they also said, "Well, we'll give you a little sample of the standard, a new powder that we just put out the market. It's a plaster-based powder. We'll give you a little sample of that just to show you. I mean, they didn't really know what we were going to use it for, but they gave us a little vase like that, made of this plaster-based powder, and we thought, okay, we're going to try it and just see if we can put glass into it and just cast it. And we put it in the kiln, and it came out of the kiln almost the same as it went in. And we thought, great, fantastic. And in the little vase, we packed it with glass billets, and in the little vase there was a little beautifully cast billet of glass. So we thought, fantastic. They don't realize that what they have here, which is a machine that's made for prototypes and not used for glass casting at all, in fact, is already set up for glass casting. You can just use it straight away. So you can just print the molds straight on this machine. So here you can design your form in CAD. You can also scan it in, but in this case you design it in the drawing package. You can then add a virtual mold skin, and then you can remove your initial pattern. So you just got the mold, and then you can print the mold. And they made some molds for us. So there's a mold there in the material. We thought, fantastic, we can just go ahead and do it. And it didn't work very well. It worked really well with the little glass, with little vase, because it was round, it was small, but with complex shape, thin shape, it's just the geometry, it just collapsed. So we thought, aha, we can just coat it with ceramic shell. That will be fine. That'll strengthen it, and it all will be well. So here we go. But that kind of worked, but not quite. See the gap here? That's the problem. The powder that was on the machine shrunk differently from the ceramic shell. It didn't shrink at all. So that created a gap in between, and those gap would crack. And although we could cast in there, that little or significant difference in the shrinkage didn't work in this case. So we did lots and lots and lots of tests of different things that we could get the same shrinkage rate as that building material. We even went into the Camborne School of Mine. It's at the same campus as us. So we went to them and said, here's the powder. The company wouldn't tell us what's in the powder because they sell it for, it's probably the same cost as cocaine. You know, it's really, really expensive. So that's obviously their business model, is to sell this powder at extortionate rates. And the last thing they want to do is to say what's in the powder. So we went to Camborne School of Mine and said, can you analyze it? And they said, yep, no problem. Here's the analysis. It's plaster, pretty much, with a few other things. But we've done tests, and we did test that the shrinkage rate was much greater than plaster, and it really wasn't just plaster. There's other things, but in their analysis, it was pretty much calcium sulfate. They couldn't see anything else, and obviously there's something in the mineral or and what do we do with that analysis? We're not scientists, so we as craft practitioner, I think we can just get on with things. I think that's. I think we have to recognize the qualities of not being scientists, that we have a knowledge of what a lot of materials do, but we don't have the theoretical knowledge. And that was kind of the core of the research. We tried lots of things that we knew had a certain shrinkage rate, and we kind of I mean, all sorts of things. From this is a good example. The orange stuff here is plastic fishing tackle material powder that you and we mixed some of that in to kind of get the desired shrinkage rate. That didn't work either. But we tried a lot of things that through our craft practice we knew might work, and we have pretty much got there now. This is a piece cast in the glass, made from the molds in the prototype machine, and so we are pretty used. We're now scaling up the pieces. So far, the pieces are about up to about 3 kilos of glass, and that seemed to work fairly well. And now we're exploring different scales. But one thing that I should say that in terms of glass casting, this could really be just like ceramic cell has been to metal casting. In terms of glass casting, this could really be quite a big thing, because normally in glass casting you use big chunky molds made of plaster and quartz, and they're heavy and use a lot of energy, and the bigger the mold, the longer the annealing time in the kiln. So to use a very, very thin skilled mold that we have in the technique that we now developed, which is down to under 10 mil, really has a great advantages in terms of glass practice. And the companies in the end trying to sell us a machine for months and months and months. In the end, they sponsored a machine to us, because we got talking to the CEO, the American CEO, and in the end said, "Yeah, that's great. You have a machine. This is really good for us, because we potentially we can sell more machines." So they gave us in the end, trying to sell us a machine. In the end, they gave us the machine. But just to finish off here, I'd like to highlight the importance of Gail's the part she played in this. In this project, her knowledge of glass, that craft knowledge, but also that she wanted to do pieces. She wanted to do creative pieces with this process, and that, to some extent, guided what we wanted to explore and what we wanted the process to achieve. So, the first picture of her, she's done terrible things to zinc. This is others exploration of. She's really into her zincs, and she wants to. In this case, she broke a piece of a zinc, and she wanted to connect the two pieces together using, making a glass piece to connect the two pieces together. You see a mock-up there in clay over there, and we scanned the end of the breaks, and we created this kind of form in the software, so we could print a piece. Or the model to mold for piece to connect these two pieces up together to create that glass piece, and there it is, the final piece with that connecting glass piece. So I think it's really important it's been critical for this project to have the craft knowledge and the craft approach to developing things, but also to have a creative practice that drives some of the kind of things that we want this process to do. That's me, and that's the end. Okay.